So today we prove monotone convergence theorem. The statement a monotone sequence of real numbers is convergent if and only if it is bounded. So the theorem is given in two parts. First part, a monotone sequence of real number is convergent if it is bounded. So suppose A and B monotone sequence of real number and convergent, then we need to show An is bounded. First part is this, and the second part we suppose An is bounded, then we prove it is convergent. So we have to show it is bounded. First we need to understand what is the definition of bounded. A sequence is bounded. The definition of a bounded sequence I have explained, but I remind you. A sequence An is bounded if there exists m positive real number such that absolute value of An less than equal to m for all n. This is bounded. That means we have to show that some real number we need to find such that for all n absolute value of An less than m. So the given part, this sequence is convergent since An is convergent, therefore by definition, monotone increasing or decreasing whatever, but it is given it is convergent. So by definition of convergence, for each upside positive there exists m in n such that absolute value of An minus a less than epsilon for all n greater than m, where a is the limit of the sequence. So now this can be written a minus epsilon less than An less than a plus epsilon for all this. This means if I want to remove this, what happens? This means a minus epsilon less than, if sequence is suppose increasing, then am plus 1 and the bigger term lie between a plus epsilon. So here we can see that these numbers for in and A1 A2, A3 up to am minus 1 lie outside the interval a minus epsilon, a plus epsilon. These points lie outside the interval. So I take, let m is equal to, these points are outside, so I take m is equal to a1, this is maximum of a1, a2 up to am minus 1, or this and this, a minus epsilon, a plus epsilon. So because all other points are bounded by these two numbers, so whatever may be the maximum out of this or from this, that number is m. So in this way, these are bounded by this interval and this point are also have been considered. So we have finally a n less than equal to m for all n. Hence a n is bounded, or you can say every convergent sequence is bounded. So half part is done. So now we prove the second part of the theorem. Let an be a monotone increasing sequence bounded above. Then we have to show an is convergent. So actually, why I take the monotone increasing? Monotone includes increasing and decreasing both parts, but so I take increasing, then I have to take bounded above, because the monotone increasing sequence will increase from left to right. And if I remove the boundedness, then sequence may not be convergent. So let X be the set of terms of sequence an, n belong to n. Then the given is therefore X will be bounded and by completeness property X has supremum. So let U is equal to supremum of X. Then for any epsilon positive, U minus epsilon is not supremum, then by definition of supremum, there exists some element of X which will lie between U minus epsilon and U. Then for some n greater than m, or you simply can say some element after m, or you also can say that you will find some m which onward such that U minus epsilon less than am plus 1, am plus 2, so on, lie between U minus epsilon and U. And because epsilon is positive, so U is always less than U plus epsilon. Therefore, I get the result U minus epsilon less than am plus 1, am plus 2, so on. This is simply less than U plus epsilon. Now, how can I write this? I can write this U minus epsilon less than an less than U plus epsilon. Now I replace am plus 1, am plus 2 and so on by an. Therefore I have to write along with n greater than m. So this will ensure us that these elements after m or m fall between these. So I can enclose this simply I can enclose this. How? This can be written. This can be written U absolute value of an minus u less than epsilon for all n greater than n. And this is by definition of convergence. So you can say a n converges to u, or limit of n approach to infinity, a n is equal to u, and where u is supremum of x or supremum of a n belong to n. So here this is the case I took increasing sequence, and similarly I can prove if monotone decreasing sequence bounded below. And geometrically, how can we understand this whole thing? This thing, if this is the real line, because sequence is increasing, so this will move from left to right, an, a2, a3, and so on. But because it is bounded above, so there exists some u here, which is the supremum or least upper bound. So if I subtract some number, these all terms cannot exceed u. So if I subtract a very small number, epsilon, then it will come here, and if I add some positive number in u, then it will move. Now the sequence keep going on, a4 and so on. Suppose here am, and here is am plus 1, and so am3, am4, like this, term fall between this, and this give the result u minus epsilon less than am plus 1, so on, u plus epsilon, and from here you know how I get this result. So this is the theorem, and one part, the other part, if I take other part, that an is monotone decreasing sequence bounded below, then it is decreasing sequence. So decreasing sequence will move from right to left. Then let x is the set of terms of sequence an. The same logic, because sequence is decreasing, so or since an is decreasing, therefore x is bounded below, not therefore, and by completeness property, x has infimum, say w, that is W is infimum of X. I mean geometrically, I tell you just simply geometrically, if sequence is decreasing, so the first term this, then this is A2, this is A3, and because all terms are bounded, therefore there will be W. So similarly, if I add something, W plus epsilon will move on right side and W minus epsilon will left side, but because sequence terms keep coming here, so here will be AM plus 1, AM plus 2, that again I get the same type of result. W minus epsilon less than AM plus 1, AM plus 2, and so on, and here is W plus epsilon, and this all terms I can represent by a single term like this, U minus W minus epsilon less than AN less than W plus epsilon for all n greater than n. As m increase, so this again I can write AN minus W less than epsilon for all n greater than m, and this mean AN equal to W. So this decreasing sequence will converge to infimum. W is what? It is infimum of X. So it is simple.